In video 59 of Tensor Calculus, we'll take a look back at prior results to see that most of them are universally applicable to all manifolds. This will establish a solid baseline as we move on to explore topics that are unique to cases where the manifolds are non-Euclidean. In this video, what we're going to do is take a look back at a number of previous topics. I'm not going to derive anything new, we're simply going to reference things we've already done. Now, of course, you already know that everything we've done applies to a plane surface. So I have restructured the syntax to reflect the fact that we're dealing with surface coordinates in 2 dimensions instead of 3 dimensions. But what I want you to do is to imagine now that we're going to relate these topics to curved surfaces. Now, in each case, what I've done is to give you a reference number here. And that reference number is the video number where we derived the initial concept. So what you can do is go back to any of these videos and get a more in-depth understanding of how we derived and developed the topic. And the point is that that derivation or that development works exactly the same way for curved surfaces as it does for Euclidean space. You'll see in each case that there's no reference at all that requires the derivation to be limited to a Euclidean space. Okay, so we're going to go through these pretty quickly. You already know, for example, from the last video that we can use what we did in video number 9 to derive covariant basis vectors. The same technique. It's the partial derivative of our position vector. Okay, now that leads naturally to the fact that we have a way of establishing linear combinations. We can combine these basis vectors with vector components. Let me point out that everything we say here is going to be relative to vectors in the tangent plane. We're not going to deal with vectors that are outside the tangent plane in this video. So as long as the vectors are in the tangent plane, we can establish a linear combination. All right, the next thing that we did along the way was to see that we have the ability to express things in either the S system or the S prime system, just like we did with Z and Z prime. The two are related by a transformation, and that led us to the fact that we were able to define the Jacobian. And the Jacobian is simply the partial derivative of S alpha prime with respect to S alpha. And with that definition, that led us to the knowledge that there are 2 different types of transformations, a covariant transformation and a contravariant transformation. So all of this is back in video number 11. Now remember that a covariant transformation is one where the free index is on the bottom, and a contravariant transformation is one where the free index is on the top. So those relationships all continue to exist with curved surfaces. All right, we also learned in video number 13 that the Jacobian has an inverse, and if we multiply, do a contraction of the Jacobian with its inverse, then we'll get a Kronecker delta like this. Remember how this works. You look for the dummy index in each case, and the Kronecker delta is formed by the remaining 2 indexes. Doesn't matter which one is primed or unprimed or what the order of the factors are, but the Jacobian contracted with its inverse will give us a Kronecker delta. All right. The next thing we did was to define what we call a covariant metric tensor. This was done in video 15. And the same thing happens in 2-dimensional curved surfaces. A covariant metric tensor is just the combination of all the possible dot products between our covariant basis vectors. And because this operation is commutative, these indexes are symmetric. Okay, next thing is we went to video number 17, where we developed the concept of the contravariant metric tensor. And there we defined the contravariant metric tensor as the inverse of the covariant metric tensor. So the contraction of these two gives us the Kronecker delta. That we used in turn to define the contravariant basis vector as a linear combination associated with a covariant basis vector. Okay, now one quick word here. Because the covariant basis vector lies in and defines the tangent plane, that means that all the linear combinations you can form with that covariant basis vector will be in the tangent plane, and that guarantees us that the contravariant basis vector also lies in the tangent plane. So the contravariant basis vector is an alternate basis for vectors that lie in the tangent plane. And you see that down here, that we can form linear combinations using either the covariant basis or the contravariant basis, same way we do for Euclidean space. And all of the properties that we derived back there continue to work here. The dot product between a covariant and contravariant basis vector gives us a delta function. If we take the combinations of dot products of our contravariant basis vectors, we'll get the contravariant metric tensor. All right, all that continues to work as is. Okay, in video 19 we talked about the definition of a tensor. Well, that continues to work in any situation. A tensor is one that transforms. It's an object like this that transforms using these sets of Jacobian factors. There's one for each contravariant index here, and there's one for each covariant index here, and these free indexes match here, these free indexes match over here, so all that continues to be true no matter what the dimensionality or whether the space is Euclidean or curved. All right, all the properties of tensor algebra continue to work. We can add these things as long as the index structures are the same. We can multiply by scalar factors, and we can combine them together. The whole thing is a linear operation. Likewise, the concept of tensor products and contraction, all of that continues to be valid. You can go back to video number 21 and see how all of that works together, that if P and Q are tensors here, then R is going to be a tensor as well. Note that we're contracting the beta index here. So all of that continues to be true. All right, that led us naturally to the idea of raising and lowering indexes. So all of those concepts are true. We can use the contraction with our metric tensors to take an index like beta and raise it up into this position, or we can take one that's in the upper position, use the covariant metric tensor, and lower the index as we do here. And then all of the more advanced forms of it work as well. So we can use it to raise more than one index at a time in any order, and all of the syntax with using the dots for placeholders, all of that continues to work as we described it back in video number 22. And then the idea of flipping the indexes, where we can raise one index like alpha here if we lower it in this position, and likewise we can raise and lower everything as long as we do them in unison. Okay, next we developed the idea of a dot product, and again we're dealing only with vectors that lie in the tangent plane, and if we do, then the concept of a dot product continues to be valid, and we developed that idea in video number 24. So let me take a minute to point out the fact that absolutely everything we did in the first 26 videos of the series is applicable to all manifolds. You can safely apply everything we did there in all cases. It's when we begin to do a study of the covariant derivative that we're going to run into some situations where we have to make adjustments. However, there are more things that we can look at. Because we jump forward to determinants, we'll find out that most of the topics with determinants continue to hold true as well. So let's move forward to video number 43, and you'll remember that's where we talked about the permutation symbols. Well, those are applicable to everything as well. We've already talked about how those look in two dimensions, so the definition of our permutation symbol follows the exact same form as we talked about in video 43. Okay, that in turn leads us to these relationships for determinants. We still have each of these relationships that work fine, and of course I've expressed them in the forms they would look in two dimensions. So you might go back to video 55 to remind yourself of how we have to make adjustments for the number of dimensions when we talk about determinants. But none of this precludes the application to curved spaces. All right, moving forward then, what's next? We had video 46 where we talked about the concept of relative tensors. We found out that the permutation symbols are not tensors in the sense that we've been studying them. They're relative tensors. This one has a weight of 1 and this one has a weight of -1. Well, that continues to be true in curved surfaces. All of these relationships continue to hold true. If we have determinants, if the indexes are mixed, then we have an invariant expression. If the two indexes are on the bottom, then the relationship is a relative tensor with a weight of 2. If the two indexes are on the top, it's a relative tensor with a weight of -2. Okay, the topic of cofactors that we studied back in video number 47 is true. Again, the only difference here is that everything has been expressed in two-dimensional form. But all this stuff continues to work even if the space is non-Euclidean. So we have the definition of our cofactor as either this derivative or this expression. And we have the fact that the cofactor is proportional to the inverse of the determinant. All right, then we have the idea of the volume element that we studied in video number 48. Remember that it's a weighted relationship. It's the absolute value of the Jacobian that relates the volume element in the prime system to that of the unprimed system. And finally, that led us to the Levi-Civita symbols that we defined back in video number 51. So we take the permutation symbol and combine it with the volume element to define the Levi-Civita symbol. And these continue to work in all cases. Okay, with that I think I've made my point. Everything I've shown you in this video is true for all manifolds in general. We're free to use any of these results as we move forward to develop topics that do need to be extended or modified to accommodate non-Euclidean manifolds. We'll begin that process in the next video where we introduce something that is new and unique to submanifolds, and that is the shift tensor.